One of the problems society is facing is that we are emitting too much CO2 into the atmosphere now, which leads to all kinds of unwanted effects. Global warming, erratic weather patterns and such. An obvious change is switching to renewable energy sources such as solar and wind. Another approach is to take the CO2 that we are producing anyway and use it as a feedstock and use again renewable energy to turn that CO2 back into useful chemicals and fuels. The synthesis of transportation fuels from CO2, you can also think of the synthesis of all kinds of chemical intermediates that the chemical industry can use to generate polymers and other chemicals that we have around us in our daily life. Presently, all these chemicals are derived from fossil fuels, but by using CO2 as a feedstock, we again emit less to the atmosphere, which will help us to come to a more sustainable world down the road. Using CO2 as a feedstock sounds like a great idea, but of course we're not doing it yet today or only in very limited ways. And that is because the technology to turn CO2 back into these chemicals is only starting to be developed. And over the last decade, lots of people, lots of researchers at companies in academia have started to pursue this problem because they see the opportunity. And catalysts and electrodes have been developed that can do some of these conversions. So the activity of the catalyst and the selectivity of the catalyst towards the desired product, we're making really good progress on that. The challenge, however, is to look at how do we turn these promising catalysts into a commercial technology. Of course, a commercial technology needs to operate for many thousands of hours. So one of the problems we're trying to address here at the EBI is to look at catalysts and electrodes and making them durable, so we can build larger systems, larger electrolyzers that can operate for thousands of hours and be very energy efficient. Specifically in this EBI project, we are trying to turn CO2 into carbon monoxide, which then can be turned into fuels using a process called Fischer-Tropsch. That's already well known, a synthetic fuel process that has been developed in the Second World War. Over the last decade, researchers such as us at the EBI as well as others have been able to drastically improve the activity of the catalysts, so the rate by which they can convert CO2 into a desired chemical. Second, of course, a catalyst needs to be selective, so it only makes the product you want. So there's different catalysts that can make different products. So carbon monoxide, for example, use silver nanoparticles. But if you want to produce ethylene, which is a starting material for polymer synthesis, you would use copper-based catalysts. Progress in CO2 conversion has been such that companies have started to look at taking the results produced in academia and turning them into technologies that they can start testing at scale. And many people in academia and industry have started to do economic analysis of what it would take. How good of a catalyst, how good of an electrolyzer do we need to create a system, or in the end a plant, that can operate in an economically feasible way. And when it comes to catalyst activity and selectivity, we're about halfway there. Further improvements are necessary, but we're pretty good already. When it comes to durability, however, the present catalyst and especially the present electrodes are not durable enough to allow for operation over thousands of hours, which of course will be necessary in an industrial plant. So the overall idea is to use renewable energy and drive the CO2 conversion process electrochemically and then create the chemicals that you would want for either fuel production or chemical production, for example ethylene for polymers. So an electrolyzer always has two electrodes. For example, in a water electrolyzer, on one side you produce hydrogen, on the other side, in the other electrode, you produce oxygen. In a CO2 electrolyzer, on one side, the cathode, you turn the CO2 in a desired product, and on the anode, a reaction takes place that's called oxygen evolution. Another challenge in CO2 reduction via electrochemical ways is that CO2 reduction is happening on one electrode, the cathode. On the other electrode, typically we perform a reaction called oxygen evolution. However, oxygen evolution takes about 90% of the energy, of the renewable energy you use to drive the process. So one big research opportunity is to come up with alternative reactions for this other electrode, the anode side, so you can reduce the overall energy need of the process of CO2 reduction and thus make it much more energy efficient.